Hey guys, I'm Cyborg Sheep, and welcome to the Weekend Post. When I closed out my video explaining logic gates, I thought it was as simple as, okay, let's get a bunch of chips and a relay, chuck a circuit together, replace this switch, and we never have to think about turning the light on and off again. But it wasn't. So like any electronics project, our story starts with the breadboard. I stuck all my chips onto the board and tested each one as I wired it up, and the output was actually pretty close to what I was expecting. Then I added the counter chip, and this is where things started getting weird. Sometimes it would count up and count down exactly as I wanted it to, but other times I would be getting false counts all over the place. Which, to put it in simplest terms, is I would trigger the increment pin, and instead of adding 1 to the count, it would add 2 or 3, or it wouldn't count at all. And being that the goal of this circuit was to maintain as accurate of a count as possible, there was just no way that this was going to work. So I thought it was my knowledge, or lack thereof, of these dual inline package chips, and that I had wired it wrong. But then the mystery deepened. So this weird false count nonsense happened with a simple switch circuit like I have here, which has a relatively pedestrian on-off control. So in the circuit, I tried all the classical mitigations. I tried putting decoupling capacitors on the input of the counter. That didn't work. I went down a rabbit hole putting 10K pull-down resistors on every single input on my chips. That didn't work. I even went as far as replacing the breadboard I was using with one that isn't complete junk like this one is. And from the start, this could have been a significant source of problems. Because in these cheap breadboards, the contacts are made using very flimsy metal. And with plugging and unplugging wires non-stop, the contacts wear out a lot faster compared to these nicer breadboards here. And if you're interested, Ben Eater on YouTube, I'll leave a link in the description, has done a video on these breadboards. He dug into them and shows you why they're so garbage. They're crap. But unfortunately for my situation, switching the boards wasn't able to solve the problem, and I only saw a minor improvement to the aforementioned false counts nonsense. Which then led me to the suggestion, gee, why don't we take a look at these sensors? But then, get this, I got the same random failures using these sensors, and that seemed to suggest that these sensors were at fault. And this is ultimately why I decided to make this video, and even more so, why I decided to embark on this project. Passive infrared sensors have an output signal that is so inconsistent that, for a lot of spaces, particularly offices, an installation of these devices becomes a rather large engineering challenge. And when you take 2 or more of these sensors, you now have double the problem. Because let's look at it this way, even with both an increment pin and a decrement pin, I still need an additional 5 chips to decode the data from these sensors. That's ridiculous, and even a microcontroller is going to be on the struggle bus when it comes to that much inconsistency in the data. Because here's how a typical installation of one of these sensors would work. Initially, the room is empty and the lights are off. Then, the sensor detects someone entering the room, and it does this by measuring the small amount of heat radiating from objects. The sensor knows it has detected motion when a heat-radiating object passes between 2 of its heat-sensitive zones. And when that happens, a comparator integrated into this amplifier chip detects the sequential signal and knows to turn the output of the sensor on, thereby turning on the lights. But here's the problem we're running into. Once the heat-radiating object leaves the sensor's field of view, there's nothing to keep that sensor on other than the difference in heat signature between the sensor's 2 elements. And necessarily over a short amount of time, the sensor's elements will cool off and the output will shut down. Now this in and of itself is not a problem, but the inherent randomness, the unpredictability of this process is. And it can vary drastically depending on how long the sensor is triggered for and which direction the object moves. And unless there's additional circuitry keeping that relay powered, that output signal will disappear. The relay will shut off, and the whole train will come to a screeching halt. And that is why it's easy to use the output signal as a trigger for a timer circuit, but as soon as you have a logic circuit, where it's a timing critical application, and you need one sensor to turn off before another one does, actually demanding any accuracy from the sensors, you'll get crippling failures all over the place. But the overarching problem is that timer circuits are far from a perfect solution. Because in an office setting, for example, getting the timer setting just right is almost impossible. If the timer setting is too short, then the lights are more than likely going to turn off with someone still in the room. But if the timer setting is too long, then there's no point to even having a motion sensor because you lose out on the benefits of extended bulb life and power savings. All this buggy behavior and random observation is to say, I haven't actually been able to put together a working prototype yet. And the reason I haven't been able to get it working is specifically these two sensors right here. These are Parallax brand sensors, and despite having the aforementioned amplifier and comparator, there isn't any way to control the length of the pulse produced by the output pin. Instead, the length of the pulse is exclusively determined by the unpredictable nature of the elements inside the sensor. And to demo what is happening here, I rigged up this simple circuit with these LEDs. And the way to interpret these LEDs is that if only one of them flickers, then everything is working fine. The length of the pulse between the two sensors is close enough to identical that no issues are caused. But if the length of the pulse between the two sensors is drastically different, then one of the LEDs will flicker, and then the other one will flicker, which is not right for what I need to output. So, that is not normal. And that is normal. Which then leads me to the question, why did Parallax design these this way? Keeping in mind, of course, that these sensors cost more than double what these sensors cost for what I'd say is basically inferior functionality. I don't know, but much like my stepper motors project that I did, it's a work in progress, and there's still bugs in the system to work out. But with transitioning to these breadboards with a nicer construction, I think I have a pretty clear path going forward. So, I think with that, I'm going to leave the video there. Hit that like button if you liked it, subscribe if you're new, and I'll see you dudes in the next video.